Welcome to the lecture series on image recognition with neural networks. This is lecture 6, where we'll be writing the entire image recognition program in Python. Here are the objectives. We'll write the entire program that recognizes handwritten digits. We'll talk about what we didn't cover in the lecture series and what we'd like to cover possibly in a future lecture series. In the last lecture, we talked about mini-batch gradient descent. Here's the basic algorithm. We want to optimize W1, W2, B1, B2, but we don't know what they are initially, so we're going to just randomize it. Then we're going to look at the entire data set, which is 50,000 images, 30 times. Each time we look at the data set, we're going to shuffle the training set, pick out 10 images. Then using those images, we vectorize it by creating X and Y, which is matrices of images and labels. Then we're going to feed forward the 10 images, X, to get the intermediate variable, Z1, A1, Z2, A2. Then we're going to backpropagate to find the gradients. Remember, the gradient is the direction of biggest increase, so we want to go in the opposite direction of the gradient to decrease the cost. And so for example, one step of that is taking the old randomized W1 and then move in the direction opposite of the gradient, which is the minus sign, and then the step size tell you how big of a step to take. And so we keep doing this to continually find and adjust our parameters. So here's the code. So here's the entire program. I want to point out again that the lecture series is based on neural networks and deep learning by Michael Nielsen. And so the entire book is free online. I really encourage you to read this if you want to get more details. Okay, so a lot of this has come from the previous lecture, so I've just copy and paste a lot of the code that we did previously. So this is to import the data. And then this cell here helps us graph the images. Here's a prediction function from I think lecture 3. We talk about the sigmoid function. And then the sigmoid prime function is the derivative of the sigmoid function. And so sigmoid prime, again, you can track this. If you've done calculus, you can show that sigmoid prime is the same as the product of sigmoid of x times 1 minus sigmoid of x. So here's the sigmoid prime function, and then this is the classifier. This is the score function given to the image x, and the parameters. Again, the first lecture we used the optimized parameter to make prediction, and so given the parameters, we can find the prediction by doing a matrix multiplication, adding the B1, applying sigmoid. We're doing this twice because this is a 2-layer neural network, and then so A2 is the prediction vector. And then in one of the lectures we talk about vectorizing, which is taking a mini batch and then put it into a big matrix so that we can apply the feed forward network only once rather than doing it using a for loop. And then this is the for equation of backpropagation that we talked about in lecture 5. We'll use those to find the gradients. Okay, so here's the main function for gradient descent. The input is the training data, which is 50,000 images. Epoch is 30 for us. We're going to look at the entire data set 30 times. Mini batch size is 10. The eta is the step size, and then the test data will help us see how accurate our model is. We're going to use the test data every time we look at the entire data set once to kind of see how we're progressing. Okay, we're going to let n be the length of the training set data. Again, that's 50,000. The n test is the length of the test data, which is 10,000 images. Now, the test data is the data that the computer has not seen. Okay, so here's how we're going to do this. We're going to randomize the data. So first, we have to randomize these parameters. So we use the ran in function from the NP library. So okay, this is 3784. This is because our image is 784 dimension and our hidden layer is 30. So that's the W1 matrix. W2 matrix is Then we're going to go from 30 dimension to 10 dimensions. So that's W2. This is for matrix multiplication. B1 is the column vector, and so this will have dimension 30, 1, and then B2. We'll talk about the dimension in the second lecture. So this is 10, 1. So again, we want to find the best profit parameters. As of right now, these are randomized. Okay, so here's the outer loop, which we go to. This is 30, so we go through the entire data set 30 times. Each time we shuffle or randomize the training data. So here's the inner loop that look through the entire data set and pick out 10 images at each time. So look at for each k in from 0 to n, and we're gonna, the step size is the mini batch size. So for example, k will be 0, 10, 20, 30, etc. So let's take out a mini batch. So we look at the training data, and we do slicing to go from k to k plus the mini batch size. Okay, then here's how we're going to feed forward. Actually, before that, we have to vectorize it first. So vectorize mini batch with mini batch. So again, X is the 10 images, Y is the 10 labels. Okay, so here's the feed forward. Z1 is NP dot, this is the matrix multiplication, W1 with X plus B1, and then A1 is applying sigmoid. This is the one layer, Z1, and then we do this again. Z2 is multiply W2 with A1, the previous result, and then add B2 to it, and then A2 is applying the sigmoid function to Z2. And then now we have to backpropagate. Again, this is also vectorized. So we first find DJ dz2. Okay, so again, this is the 4 formulas right here. L for us is 2 because we have a 2-layer neural network. And so M is the mini batch size, so this is A2, which is the prediction minus the label times element-wise multiplication. This is the O dot sigmoid prime of ZL, which is the intermediate layer Z2. So we reduce that. We're going to say 1 divided by mini batch size. So we want the A2, which is the prediction, minus the label, times by sigmoid prime of Z2. And then we're going to use that to find DJD W2. So that means we use DJD Z2 and multiply by I minus 1 transpose. So now we're going to find, so this is, so again, this is DJDZ2 times A1 transpose. So this is DZ2 times A1 transpose. Then DB2 is, so here's the formula again. So if I know DJDZ2, I can add up the columns of that matrix, divide by M to find DJD B2. And so again, add up the column, we use NP sum and use an Axios trick, right? So this is NP sum. Actually, you have to divide by the mini batch size also. So we're adding up the matrix DZ2, and we want to use Axios 1 because we're adding up the columns of that matrix. Then we want to keep the dimension again, NP sum will collapse the matrix into a one-dimensional matrix, and so we want to keep everything in 2 dimensions. So that's so that all the matrix multiplication works out. Okay, now this is now we've found the second layer derivatives, the gradients. We now backpropagate to find the first layer, which is now dz2. So here's the formula we're going to use. If I know dj dzi plus 1, I can use that to backpropagate and find dj dzi, which is the previous step. So this is the transpose of the w times the dj dzi plus 1. Element-wise, that was sigmoid of z2. So I'm going to do that. So here, this is 1 divided by the mini batch size. And then this is np dot. Again, this is wi plus 1 times dj dzi plus 1. So that means that this is w2 transpose, and then dz2 sigmoid prime of z1. And then dw1, again, this is the same formula as the previous step. So this is dj dz2, so this would be dj dz1, and then this is x transpose. And then finally db1 this is similar. We're going to use that NP sum trick, so it's 1 over mini batch size NP dot. So it's dz1, and then axis is also 1. Keep the dimension. I think that's it. So now we found the gradient, the direction that we should walk to increase the cluster mode. So you want to take the opposite direction. So this is now we're going to update the parameters. So for example, W2, this is take the old value, go in the opposite direction, this step size, and then the gradient is dW2. So that's just the gradient direction. And then we do this again for the other parameters. So now, for example, W1, we take the old value of W1 and go in the opposite direction of W1. Same thing here. Now this is, say, W2. Take the old value of B2, and then the gradient of B2. And then finally, finally B1 is B1 times DB1. So that's the updating of the parameters. And then that's it. And then I have here the code from Michael Newson that allow us to test after every epoch. Basically, feed forward the network with the x and y, where x and y comes from the test data, and then measure the accuracy of the prediction, which is given by the model with the argmax, and finding out whether the prediction match up with the label, and then displaying the accuracy. And then we return the optimized parameters once we finish with the training. Okay, let's see if we can run this. So we're going to run, here is run the entire, run all. Okay, so there's some error here. So many batch, so DB1. Oh, sorry, this is NP sum, not NP dot. There we go. Try that again. Okay, hope this works. There it is. So after the first epoch, which is look into the entire training set 50,000 times, we have an accuracy of about 82%. So 82, about 82 to, I guess 81%. And notice that as we look at as we look more and more of the data, the accuracy increases. And so after looking at the training data, for example, 7 times, we have about 91% accuracy. So this is pretty amazing that using this gradient descent, we can continually see improvement over our parameters and reducing our error and thereby increasing the accuracy of our model. If you remember from lecture 1, I gave you the parameters that allow you to make prediction on images. Well, this is the place where we found those parameters. I basically saved the parameters from a training session like this, and then upload it into lecture 1's notebook. And so we do this 30 times. So as we get to epoch 29, it'll stabilize to around 94, 95%. And then once we do that, we can use those parameters that we get from training the data, training the program to make prediction. And that's what we're going to do once we wait for this to complete. By the way, we didn't do this with vectorization. For example, Michael Newton's code will be a lot longer to train this, but because we vectorized it, this is actually pretty fast. I think I measured it to be about 3 or 4 times faster than the unvectorized version. So here it is. So now that we have the parameters that we saved, we can now make prediction. So using these newfound parameters, here's the prediction, and let's check to make sure if that's accurate. There it is. So this looks like gets everything right. Okay, congratulations. So that's basically the entire code. So hopefully you've tried to do that on your own in lecture 5, but if not, you can look at this video and find your mistakes. Okay, so this is basically the end of the lecture series. So I want to talk about what we didn't cover. So we didn't cover hyperparameter tuning. I mentioned this a lot during the lecture series. We kind of were given all the parameters. For example, we used a 2-layer network. We used 30 for the epoch, and all those. The step size also is all given. But technically, we have to find those on our own. And we didn't talk about overfitting, which is basically when we do well on the training set, but we don't do well when we look at new data. And the way we fix that is use something called regularization. We also didn't talk about using a library to do this. We did everything manually, which is a lot of calculus, but in practice, people usually don't use all this calculus by hand. They use TensorFlow or some kind of a library to do all the derivatives for us. Okay, what's next? There's a lot of things that I want to do in the future. So for example, I want to do a tutorial on TensorFlow and see how we can write this entire program without using all those calculus formulas. When we want to talk about image recognition, really convolution neural networks is the way to do it. We basically only do a basic fully connected neural network, but maybe something in the future we can talk about CNNs. Recurrent neural networks is also very popular, especially when it comes to things like natural language processing, handwritten recognition, things like that. And then there's also other machine learning algorithms. Linear logistic regressions are basically the same thing as what we talked about, but maybe more detail on some application of those. And then also things like support vector machines and trees and all those other algorithms. So again, hopefully these are the list of things that I can talk about in the future lecture series. Thank you for watching. And again, if you like this video, please subscribe, like, or share these videos. And hopefully I'll see you soon in a future video. Again, here are the final references, Michael Newton's book, and then the vectorized version, actually, I got it from Andrew Ng's course on deep learning. Okay, thank you for watching.